Well, hey everyone, and welcome back to Maths. I hope you're all having a lovely day today, and we are going to be doing some groovy practice problems that I have prepared just for you. So today we're going to be practicing greatest common factor, which was the topic of the last lecture video, where we discussed what a greatest common factor is and how we can use prime factorization to find it. So we're going to be practicing those ideas and getting really comfortable with them. So you know the drill by now. Pause the video, give it a shot, and we will do them together once you've done that. Alright, so for question 1, it's just a bunch of greatest common factor problems. It wants us to find the greatest common factor of the following pairs. So let's start with GCF, which stands for greatest common factor, of 30 and 66. So to do this, what we had to do is find the prime factorization of both of these numbers, which would allow us to basically get all of the factors which we've discussed in a previous video, and then we can use that fact in order to basically find all the common prime factors, which is then going to give us the greatest common factor. So let's go ahead and prime factorize these bad boys. So 30, that can be split up into 5 and 6, right? 5 times 6 is 30. 5 is a prime number, so that's going to give us one prime factor. And then 6 can be split up into 2 times 3, both of which are prime. So that means our prime factorization of 30 is 2 times 3 times 5. Awesome. Now let's do 66. So 66 is 6 times 11, right? We know that from our times tables. And 11, that's a prime number. Awesome. And 6, just like over here, can be split up into 2 and 3. So that means the prime factorization of 66 is 2 times 3 times 11. So now to find the greatest common factor, all we have to do is just circle the common prime factors. So 2 is common to both of them, and they also both have a 3. So that means our greatest common factor is going to be 2 times 3, or 6. Let's go on to part B. So I have some bigger numbers here, but we're still going to have some fun with it. So let's not be frightened by a few extra digits, we're better than that. So we will start with prime factorizing 250, right? To find this greatest common factor, we got to get the prime factorization of each of these. So 250, well, that is the same thing as 50 times what? Well, 50, 100, 150, 200, 250, right? Just going up by 50s. We have to do that 5 times, so we get that 50 times 5, which is a prime, gives us 250. And now we can prime factorize 50 into, let's go with 5 and 10. Alright, so we can get a 5 out of that, and 10 we can split up into 2 and 5. So we see that 250 is 2 times 5 times 5 times 5, right? 1, 2, 3, 5s. So that gives us 2 times 5 cubed. Great. So now let us prime factorize 348. Alright, so we can split up 348 into 2 and 174. Alright, 170 times 2 is 340. 4 times 2 is 8, so that'll give us 348. Good. And 2 is prime, so we can square that off. And then 174, we can split that up into 2 times what? Right, because it's even, so we know we can pull out a 2. And that's going to be 87. Right, 8 times 2 is 160, 7 times 2 is 14, 160 plus 14 will be 174, so that's how I know that 2 times 87 gives me 174. Now is 87 a prime? Well, a lot of numbers that end in 7, I mean, those might be prime, right? Well, if we add up the digits, 8 plus 7, that's 15. 15 is a multiple of 3, so that means by our rule that we discussed in a previous video, 87 has to be a multiple of 3. So what do we get? Well, it's going to be 3 times 29, right? Because 3 times 20 is 60. 3 times 9 is 27. 60 plus 27 is 87. So we get that 3 times 29 is 87. And both of those are prime factors. So we are going to get that the prime factorization of 348 is 2 times 2 times 3 times 29. And if you didn't believe me about any of these pairs here, you can go ahead and verify for yourself. I always encourage people to do that. Alright, and we have two 2's here, so we can also write that as 2 squared times 3 times 29. Alright, so now let's go ahead and circle all the common prime factors. So 2 is common, and, well, that's actually it, right? We have just 5's here, and there's no 5's here. So 2 was the only single prime factor that appeared in both of them, which means that the greatest common factor for 250 and 348 is going to be quite small. It's just going to be 2. All right. Well, big numbers doesn't necessarily mean a big common factor, it would seem. So let's do part C. Let's find the greatest common factor of 140 and 200. So you're probably getting pretty good at this prime factorization by now, but let's go ahead and do this anyways. So 140, we can split that up into 70 times 2. 2 is prime. 70 we can split up into 7 times 10. 7 is prime. And 10 we can split up into 2 times 5, both of which are prime. So that means our prime factorization is 2 times 2 times 5 times 7, which is just 2 squared times 5 times 7. All right, man, we're just killing these. We're just so fast. All right, so 200 we can split up into 2 and 100. Boom, prime factor. 100 we can split up into 2 and 50. Boom, prime factor. 50 we can split that up into 5 and 10. Oh, prime factor. And 10, well, that is going to be split up into 2 and 5. Now we have all prime factor leaves, you could call them, because we're thinking of this as like a tree, right? So the prime factors of 200 are 2 times 2 times 2 times 5 times 5, or written in our nice compact exponent form, 2 cubed times 5 squared. All right, so now let's look at the common factors. We have 2 and 2. We have another 2 and another 2. We have a 5 and a 5. And anything else? Well, here's a 7, but no 7 appears over here. Just another 2 and a 5, which we don't have more of over there. So our greatest common factor is then going to be basically this combination of prime factors, 2 times 2 times 5, which is 4 times 5, which is 20. So the greatest common factor of 140 and 200 is 20. That's the biggest factor that is common to both 140 and 200. All right, so let's prepare ourselves for D, which looks like it's going to be quite a doozy. We got 6,000 in there, man. That's a girthy number. But hey, this is Bo Maths. We do hardcore math here, and that includes girthy numbers. So let's look at the greatest common factor of 6,360. All right, so maybe we should start with the 360 because that's the small one. Nah. Let's do the 6,000 because we take the scary things by the horns. We don't have to put it off. So let's do this. 6,000. Well, that ends in a 0. It's even, right? Let's just divide this by 2 right away. All right, now we have a significantly smaller number. It's only 3,000 now, right? We've already taken it from 6,000 to 3,000, so we don't have anything to worry about. All right, let's split up 3,000. Well, once again, even number. We can divide that bad boy by 2. 2 times what is 3,000? Well, 2 times what is 30? 15, right? Add in a couple zeros. We get 2 times 1,500 gives us 3,000. But we're not done there. No, it still ends in a 0, right? So we could divide this by 2 again. But is there a bigger number we could divide this by? Well, what about 100, right? 1,500 is often referred to as 1,500, right? And that's because it's the same thing as 15 times 100. Now we have 2 even smaller factors we can work with, both of which are still composite, which means we can decompose them further into primes. 15 we can split up into 3 and 5. All right, so now we have all the primes in this segment. 100 we can split that up into 10 times 10. And these 10s we can each split up into 2 and 5. All right, so that's quite the doozy. We got a lot of prime factors here, so let's collect them all. So let's start with the 2s. We have 1, 2, 3, 4 2s. So that's 2 times 2 times 2 times 2. And then for 3s, we just have 1 3 times 3. And then for 5s, we have 3 5s times 5 times 5 times 5. And this is really showing off why exponent form is nice, because this is quite long to write. But we could just write this as 2 to the 4th power times 3 times 5 to the 3rd power. All right, awesome. So that is our prime factorization of 6,000. See, it wasn't as bad as you thought, just a little bit longer. So now let's do the prime factorization of 360. All right, so we can split 360 up into, let's say, maybe 36 and 10, right? Anything times 10, we're just adding on another 0, so 36 times 10 is going to be 360. And we can split 36 up into 6 times 6, And we can split each of those up into 2 and 3, which are both primes. All right. And now we still have our 10 to deal with, which we can promptly split up into 2 times 5, both of which are primes. All right, awesome. So we get 1, 2, 3, 3 2s, and we get 2 3s, and we get a 5. So our prime factorization is 2 cubed times 3 squared times 5. All right, so now we can go ahead and identify all of the common factors. So we have 3 2s are common in both of them. There's a 3 that's common in both of them. And there's a 5 that's common in both of them. So that means our greatest common factor is going to be 2 times 2 times 2 times 3 times 5. All right, so let's see. 2 times 2, that's 4. Times 2 is 8. 8 times 3 is 24. 24 times 5, this is all going to be 120. All right, so the greatest common factor of 6,360 is 120. All right, so that was question 1. And if you want some more practice with these, it's pretty simple. All you have to do is look at the greatest common factor, pick 2 random numbers, and find what their greatest common factor is. All right, so let's go on to question 2. I have 2 different prime numbers. What is their greatest common factor? Okay, so we don't actually know what these numbers are, so we're not going to be able to prime factorize them. And besides, they're prime numbers, right? So their prime factorization will just be themselves. So what we have to do for this is actually just consider, what does it mean to be a greatest common factor? So I'll write prime number 1 and prime number 2. So these are our 2 different prime numbers. And to be the greatest common factor, we basically just need to list what their factors are and pick the biggest one. Well, what are the factors of a prime number? It's only going to be 1 and then the prime number itself, right? So that means the prime factors of prime number 1 is 1 and prime number 1. And the prime factors of prime number 2 are 1 and prime number 2. All right, so since prime number 1 and prime number 2 have to be different, right? It says that in the problem. What's the only common factor here? Well, it's just 1. So the common factor between these 2 prime numbers is exactly going to be 1. So their greatest common factor is 1. That's the answer. All right, so that wasn't too bad. Let's go on to number 3. Kieran has a prime number and a composite number and claims that their greatest common factor is bigger than 1. Josh thinks he's silly. Who's correct here? All right, so we got another classic Kieran versus Josh problem. And what Kieran is claiming is that he has a prime number and a composite number that have a greatest common factor bigger than 1. So we saw in question 2, for 2 different prime numbers, they had a common factor of exactly 1 because, well, they were prime and they were different than each other. That's the only common factor that they had. But Kieran's saying that 1 number is prime and 1 number is composite. So clearly these numbers are different because you can't be both prime and composite. So let's see if we can think of an example in which Kieran's going to be right. So let's just choose any prime number, maybe 7, right? That's a nice prime number. So 7, that's prime. Can we think of a composite number that's going to have something bigger than 1 in common with 7? So 8 would be an example of a composite number, but it's not going to be one that has a common factor other than 1 with 7, right? Because the only factors of 7 are 1 and 7, whereas the factors of 8 are 1, 2, 4, and 8, right? So here, our only commonality is this 1. But we want a number that would have to have a bigger common factor. Well, if the common factor is to be bigger than 1, the only other option we have is for that common factor to be 7, right? Any other number, it wouldn't be a factor of 7, so it wouldn't be a common factor. So that means we need to pick a number who has 7 as a factor. So what if we went with the number 14? All right, well, 14, that's 1 and 14 is a pair, and 2 and 7 is a pair. But that means 7 is a factor of 14. But since 7 is also a factor of 7 itself, we get that the greatest common factor of 7 and 14 is 7, which is bigger than 1. So Kieran's actually correct here. You can get a composite number and a prime number that have a greatest common factor bigger than 1. And Josh needs to rethink his life choices. Let's go on to number 4 here. So number 4 wants us to list 5 numbers who have 6 as their greatest common factor with 30. So how can we do that? Are we supposed to just pick random numbers and hope that their greatest common factor with 30 is 6? Well, no, there's actually a smarter and there's a more efficient way of doing this. So let's go ahead and try that out. So let's start with maybe trying to do the prime factorization of 30, and then maybe we'll get an idea as to what we want to do here. So 30, that prime factorization, well, we can split that up into 5 and 6. 5 is prime. And 6, we can split that up into 2 and 3. Right, we actually already did this one in number 1, part A. So the prime factorization of 30 is 2 times 3 times 5. So we know that 6 is a factor of 30 because we have this 2 and we have this 3 here. Right, this 2 and the 3 are prime factors, which means that 2 times 3, or 6, is a factor of 30. All right. And now what we want to do is we want to get a number that also has 6 as a factor, which means that 2 and 3 are going to be in the prime factorization of that number. But in order for it to be the greatest common factor with 30, 2 and 3 need to be the only common prime factors with 30. So basically we can't have another 5 in the prime factorization. All right, so for example, we could start by looking at 2 times 2 times 3. All right, that's a valid prime factorization. That's a combination of prime numbers. And we see that we're going to have a 2 and a 3 in here. And that's the only common prime factors between this number and this number. And this number is 2 times 2, which is 4, times 3, which is 12. So that means the greatest common factor of 12 and 30 is going to have to be 2 times 3 or 6. All right, let's try another one. So maybe I said something like 2 times 3 times 7. All right, so once again, this 5 isn't appearing, which is what we want. We want just this 2 and the 3 to be common, which means that they're going to have a greatest common factor of 6. And if we multiply this out, we are going to get 42. All right, so that means the greatest common factor of 30 and 42 is going to have to be 6, right? So we're just constructing numbers here using their prime factorization such that they only have 2 and 3 in common with the 30's prime factorization, and these numbers we're constructing are guaranteed to have a greatest common factor with 30 of 6. All right, so let's try another one. Let's go with 2 times 2 times 3 times 3. All right, so in this one, once again, only the 2 and the 3 are common, and when we multiply everything out, we're going to get 2 times 2, which is 4, times 3, which is 12, times 3, so that's 36. So we get that the greatest common factor of 36 and 30 is also going to be 6, right? And this one wants 5 numbers, but I think you kind of get the idea. So why don't you find 2 more numbers whose prime factorization only has this 2 and this 3 in common with 30, and those numbers will have the greatest common factor of 6. All right. So let's go into number 5, which is very similar in philosophy, right? List 5 numbers who have 12 as their greatest common factor with 180. It's just some different numbers. So like number 4, I'll do 3 numbers, and then I'll get you to do the other 2 on your own. And again, there's literally infinite options here for you. Okay, so let's look at 180. So we gotta get its prime factorization. So 180, that can be split up into 18 and 10. 18 can be split up into 9 and 2, 2 is prime, and 9 can be split up into 3 and 3, both of which are prime. And then we can split up 10 into 5 and 2, so now everything has been factored down into primes. So we get that 180 is 2 times 2 times 3 times 3 times 5, or 2 squared times 3 squared times 5. All right, and we want 12 to be the greatest common factor. All right, so what combination of prime factors gives us 12 as a factor of 180? Well, that's going to be 2, 2, and 3, right? Because 2 times 2 is 4, times 3 is 12. So this 2, 2, 3 is what gives 12 as a factor of 180. So now we need to list 5 numbers that have 2, 2, and 3, but nothing else in common with 180's prime factors. So we could do something like 2 times 2 times 3 times 7. That would be valid, right? We don't have another 3 or 5 in there, so the only common prime factors here are 2, 2, and 3. All right, so when we multiply this out, what are we going to get? We're going to get 2 times 2, which is 4, times 3, which is 12, times 7, which should be 84. All right, so we get then that the greatest common factor of 84 and 180 is going to be 12. What's next? Well, we could actually just do, if we wanted, 2 times 2 times 3, right? That's a valid prime factorization, right? It's all prime numbers. And the commonalities is exactly 2, 2, and 3. So we get that 12 itself will work for the greatest common factor of 12 and 180. All right, and let's do one more, and then you can do 4 and 5 for yourselves. So let's go with 2 times 2 times 2 times 3. So this has the 2, 2, and 3 in there, but we're also putting in an extra 2, and we get 24. So the greatest common factor of 24 and 180 is, you guessed it, 12. So these are three numbers that we've constructed here that have the greatest common factor with 180 of 12. And we did it by using the prime factorization. And again, you can come up with 4 and 5 on your own. Maybe let me know in the comments what numbers you come up with. I'd love to hear about them. All right, so now let's do this last problem here. Using the greatest common factor, how can I know if one number is a multiple of the other? So what does it mean for one number to be a multiple of the other? Well, we know something like 9 is a multiple of 3, and that's because that 9 is multiple 3s, right? 3 times 3 gives us 9. So how do we know if, using greatest common factor, how can we know if a number is a multiple of another? Well, if we find the prime factorization of two numbers, and we see that the entire prime factorization of one number is present in the other, then we know it's a multiple. So let me give you an example. Let's say 24. All right, so the prime factorization of 24 is 2 and 12, and then 3 and 4, and then 2 and 2, right? So we get that 24 is 2 times 2 times 2 times 3. All right, and now let's look at the prime factorization of 12. So 12's prime factorization is going to be 2 and 6, and then 2 and 3. So 12 gives us 2 times 2 times 3. But what do we notice? We notice that this 2 times 2 times 3 is actually completely present in the 24. So the entire prime factorization of 12 is completely within 24's prime factorization, which means that 24 has to be a multiple of 12. So that's what I mean for how can we know if a number is a multiple of the other. If a number's entire prime factorization is present in another's, that means that whole number, which is equivalent to its prime factorization, has to basically be a factor of your other number, which means that this other number is a multiple of this. And yeah, so I hope that made sense to you. And let me know if you have any questions. Good work today. Have a good one. Stay groovy. And I'm going to see you in that next video.